Okay, last video in this section. An open box is to be made from a 16-inch by 30-inch piece of cardboard by cutting out squares of equal size from the four corners and then bending up the sides. What size should the squares be to obtain a box of largest possible value? We're going to knock out two steps at once, right, at the very beginning. We're going to draw a picture, and that picture is going to be the constraint. Because the constraint here is this sentence right here, or this phrase right here, made from a 16 by 30-inch piece of cardboard. That's the constraint, that we have to use that cardboard. So steps 2 and 3 together is I start with a 16 by 30-inch piece of cardboard. Then, and this isn't going to be to scale by any stretch of the imagination. Just doing my best to draw a decent picture here. Then I'm going to take that piece of cardboard and cut out squares from each corner. And so X, 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 X. And so I have to decide, because in the end it says, what size should the squares be to do largest possible volume? Well, the volume of a box is length times width times height. And so we will get to that in a moment. Then I'm going to fold up my squares, and I think I'll do that up here. Then I'm going to fold it up to make my box. And so here's my box. And it's going to be an open box. Oops, that needs to come down much further. There's my box. Okay, so it starts out 16 by 30. I fold it up, and when I fold it up, it's easy enough to see that the height of my box is going to be X, that when I fold up this side, those squares become the height. So the height of my box is X. It said volume. Volume is length times width times height. So I need these two distances right here. So let's focus on this first distance right here. And that's 30 over there. So this started out being 30. Then I cut some squares out, and I have this distance here. Well, what I cut out on either end was X, that the whole thing, this whole distance here was 30, but then I cut out those two squares, and so what's left for this distance on the box is 30 minus 2x. And that's that front distance there. Then the same thing over here. That whole distance was 16. But then I cut out those two squares again, those two squares that each had a length of x. And so what's left here for that distance over there is 16 minus 2x. And so 16 minus 2x over there. And there's my picture and my constraint. And so here, just like the previous problem, the issue here isn't so much finding the formula we're going to use, finding the equation or the function we're going to use, but really expressing the constraint. Then step 4. It said to maximize the volume, largest volume. Well, volume is length times width times height. And so we are going to get that volume is x times 16 minus 2x times 30 minus 2x. I'm going to go to another piece of paper because we're almost out of room there. Copying that down again. Four x on. Okay, again, the zero thing. It's going to start at 0. But you honestly have 3 variables here. You don't see 3, but you really do have 3 things going on here. You have a length, a width, and a height. And all of them must stay positive or can't go negative, we'll put it that way. And so for this second guy, I got to look at my length, width, and height. And all of those have to stay positive. You can't let any of them go negative. And so using 16 minus 2x. 16 minus 2x, that has to stay positive. Negative 2x is greater than negative 16, x less than 8. And so we get 8. And so someone's going to say, why didn't I use the 30 minus 2x? Well, if I'd used the 30 minus 2x, I would have gotten 15. If I put 15 here, that would be negative. 15 minus, that would be 16 minus 2 times 15. 16 minus 30 negative. And so I went to the 16 minus 2x because essentially it was the smallest distance here. And again, kind of, you can still see the picture. You can't really see the picture. Go up and look at the picture here. This was going to be the smallest one. And so I went with that one because that was going to go negative before this one. That we're looking at keeping each one of these things from going negative. This smaller distance would go negative first. So that's why I chose to work with it. I chose to work with the smallest distance because that had the potential of going negative first. And so there's step 4. Now let's simplify. We're going to multiply this out. And so just foiling that out, 16 times 30 would be 480. Yep. Minus 32x minus 60x plus 4x squared. I'm good with that. That's x times 480 minus 92x plus 4x squared. And so 480x minus 92x squared plus 4x cubed. And just turning that around so it's in descending order because it looks prettier that way. There's my function. Step 5, my derivative. And so v prime is 12x squared minus 184x plus 480. Critical number, 12x squared minus 84x plus 480 equals 0. And yep, we got to solve that guy. But one thing I do note, I believe, is everyone is divisible by 4 here. I think that's the truth. Yep, everyone's divisible by 4. So I can divide by 4. To get 3x squared minus 46x plus 120 equals 0. Now that actually does factor. The reason why I know it factors is that I've done this problem in the past and I know it does factor, but I don't remember how it factors. So because I don't remember how it factors, I'm going to use the quadratic formula. But I'm almost positive it does factor. I just don't remember how it factors. So we're not going to figure it out. I'm going to use the quadratic formula. Life's sometimes messy. And so x equals 46 plus or minus negative 46 quantity squared minus minus 4 times 3 times 120 all over 2 times 3. And that's going to be 46 plus or minus, and when you do the stuff inside there, 46 squared minus you get 676 all over 6. And so that's 46 plus or minus. And square root of 676 is 26 all over 6. And so that's 46 plus 26 over 6. 46 minus 26 over 6. That is 72, 6, 26. Which gives me x equals 12. 72 divided by 6 is 12. And 10/3. But. On the interval, which was 0 to 8, only x equals 10/3. So I have to reject the 12 because it wasn't on the interval that I needed. So there's my critical number, but I've got to do step 2, or step 6. Verify that x equal 10/3. Will, and in this case, way back when, they said we wanted to maximize. They said largest volume. On the interval from 0 to 8. Now, even though the absolute max-min procedure would be best, I'm going to go ahead and use the second derivative test just for practice. Because like I said, I'm not going to really care how you do this, just get it done. And so for practice, we'll use the second derivative test. But if you use the procedure for absolute max-min, not going to care. It's actually better in this case, but I just wanted to practice the second derivative test again. The first derivative was this, 12x squared minus 148x plus 480. So the second derivative is going to be 24x minus 184. Plug in the critical number. And what that's going to cancel, the 3 and the 24 cancel, leaving 8. And so that's going to be 80 minus 184, which is negative. That's all I really care about. It would have been nice if you could have seen any of that. So I plugged in the 10, there's my second derivative, plug in the 10/3, the 3, the 24 and the 8 cancel, leaving 3. And so I've got 80 minus 184, that's negative. And so x equal 10/3 will maximize. Remember the second derivative test, if you just think about just positive negative issues, seems to work backwards. Then answer the question. Answer. What size squares? And I'll go way back to our picture. X was the size of the squares. So 10/3 by 10/3. And that's our last optimization problem. So that's the end of this video and the end of this lecture and the end of this section.